because probably because of time, I'm not going to get to the seasonal variation part. We'll see how much time I have. And I apologize that I'm not talking about a volatile at the moon. I wanted to contribute to this, and this is what I have, and I hope you'll find it interesting. Okay. Okay, this is the reference for my talk. It's published online in JGR. So very quick introduction. In Mercury's exosphere, Mariner 10 discovered 3 species, or 2 species, hydrogen, helium, and there was an upper limit on oxygen. From the ground, sodium, calcium, potassium, and have all been detected definitively. And there's an upper limit on iron and aluminum that has been reported. And then with Messenger, we've discovered magnesium. There's a definite detection of oxygen that's in preparation. It's been shown at conferences, and we've also seen the ionized calcium, oxygen, and sodium in the what passes for Mercury's ionosphere. With Messenger launched in 2004, there were 3 flybys of the planet in 2008 and 2009, and I'm going to talk a lot about that data. And then the orbit insertion was in March 2011. We finished the first primary and actually finished the first extended mission. And I think as far as last I heard, we're still waiting word. We're in a holding pattern right now and waiting word from headquarters on the status of the second extended mission. But it conceivably can go till about 2015. I'm going to talk about data from the Mercury Atmospheric and Surface Composition Spectrometer, MASCS. It's built at University of Colorado. It's basically two separate instruments: an ultraviolet and visible spectrometer, UVVS, and all the data I talk about is going to be from UVVS. And there's also a visible and infrared spectrometer, which is used for the surface observations. Our observations are such that we only observe a single wavelength min at a time, and if we want to, so we have to scan over individual emission lines, and we have to choose which emission lines we're going to be observing. So this is an example of an observing sequence. We can observe up to, I believe, search for 6 emissions in each sequence, but we'll do, for example, sodium, calcium, then sodium, calcium, sodium, calcium as we go through along the orbit. And we're only getting single point line of sight radiances. On the right side are examples of emission lines. Sodium, as you can see, has this whopping signal. The red line is the fit to the solar spectrum. Calcium, there's much more the solar continuum is much more important, and the raw spectrum actually looks like there's nothing there, but if you subtract off the solar Fraunhofer line, then you get the black emission line there. That's just an example of what the data actually looks like. My fonts didn't go through, but daily we see this is showing the relative ease of observing different emissions based on the G value and the instrument sensitivity. So calcium is the easiest thing intrinsically for us to observe, followed by calcium plus. Other species that we can hardly observe at all are oxygen, chlorine, sulfur. What we see daily, on a daily basis, we observe calcium, magnesium, and sodium. We've also detected, as I said, Ca plus, hydrogen. I didn't mention hydrogen, and oxygen. There's a weak detection of, and the other species we haven't seen. We expected to see some things like potassium, but we have not. Potassium or iron, aluminum, but we haven't seen any of those. So on calcium, what's interesting about calcium? This is data from the flybys, from all 3 flybys. As we passed behind the planet, the spacecraft did a roll maneuver. So it started out pointed towards the dawn hemisphere, or towards the dawn, in the dawn direction, perpendicular to the Sun-Mercury line. But then did a roll through northern pointing and then towards dusk. And the 3rd flyby, it started at south and rolled through dawn and towards north. And in all 3 of those, we saw this peak of emission in the when pointed in the dawn direction. the dotted lines show what isotropic models would look like. So and as you can see, what we saw clearly is not an isotropic source of calcium. So we've modeled this using a source that's peaked at the dawn equatorial point and then drops off exponentially with a e-folding width of sigma, where sigma in these cases I'm varying sigma from 10 degrees to 40 degrees. That gives the idea of the size of the spot on the surface. And the top panels show 10,000 K models, which don't really do a very good job of fitting the data. A 50,000 K source with a width of about 25 to 30 degrees can fit all of the flyby data. And there's more data than just this, but this is one portion of it. It doesn't look very good for M3. It doesn't look very good there, and I'm going to show you why that is. But essentially, this dawn source can fit the data really well. This is looking in the tail behind the planet, where we observed out to about 7 or 8 Mercury radii. And you can see the 50,000 K source fits the data, can supply enough material out to the tail. The cooler sources just can't supply enough calcium back that far. In the M3, we saw evidence for a slight northward shift of about 5 to 10 degrees. And this is looking at, in the pole data, when we did polar limb scans, there was a clear north-south asymmetry. And so if we shifted about 5 to 10 degrees, I can match all 3 of these sections of the data really well. So again, and it's a source of about 25, a width of about 25 degrees. And then this is, I also, in the paper, I also modeled the first 7 orbits of actual data, first 7 orbits of data. This is actually the very first orbit with calcium data, and the isotropic models are on top, and you can see there's a section of that data which there's no geometry information, but that section is when the spacecraft is basically observing the dusk hemisphere, and an isotropic model overpredicts what you would see. The model with the source all completely at dawn does a very good job of matching the entire data set. And again, it needs to be 20 to 50,000 K. The tail data were really, the tail data during flybys were really useful because we don't see that far out during orbit. And so we can constrain, the 20 and 50,000 K models tend to work equally well in these data, but we needed a 50,000 K source in order to match the flyby data. And then for all 7 orbits, we got a roughly a constant source rate within our uncertainties of about 2 times 10 to the 23. That should be 2 times 10 to the 23 calcium atoms per second, all coming off from that dawn source. The goodness of fit plot is basically trying to show that the 20,000 and 50,000 K sources both kind of do equally well, and the 5,000 K source doesn't work at all. And visually, the 5,000 K source is clearly not a good source. Okay, so I've talked really fast, so hopefully it's been clear, but I want to show this seasonal variability because this is really interesting. These are going to be using...
Stand by, Matthew. I'm going to get this up and running for you.
Okay. Yeah, there was a couple quick movies. These data are all limb scans where when we're far south of the planet, near Apoapse, we scan at discrete local times over the day side. And so you can see there's very good radial coverage. We get very good radial sampling and not quite as good, not really very good, or acceptable, I guess you could say, longitudinal local time coverage. So can you go to the next slide? It's not moving. Okay, so looking at the projections of those lines of sight in the equatorial plane, we get profiles that look like this, and I can interpolate, use the data and interpolate between to get, next slide, please, to get an image. And as you can see in this image, you can't believe any of the small scale, you can't believe the small-scale longitudinal local time variations, but the large-scale structure is clear that there's this strong dawn source of calcium. If you go to the next slide, how much time do I have left? Okay.
That would be 30 seconds.
Oh, okay.
I'm sorry, no, 2 minutes. Sorry, 2 minutes.
Okay. So this is showing all of the limb scans where we have good local time coverage. And you can see that there's always this source there. It's always there. And what's interesting, next slide, please. What's really amazing is so what I've done is I fit power laws to just the dawn point, just over 6 hours local time. And this is the intercept and scale height of that power of that, I'm sorry, it's not a power law, an exponential. This is the intercept and scale height of the exponential, covering over 8 years worth of Mercury data, and it's repeatable from year to year. This is plotted versus true anomaly angle. Each year, it looks exactly the same. I mean, just amazingly consistent. The scale height has higher spread because it's a little, I guess it's a little fuzzier, but you can see in the intercept there's a clear annual dependence, the same from one year to the next. The peak is at about 20 degrees or so, true anomaly. Just before 180 degrees, there's a little bump in there, and I'm 95% sure that that is not real. It's due to an assumption that I make in converting this to column density. Basically, it has to do with removing the G value, that there's uncertainties in the G value, which I've corrected for partially, but not completely. And then there's also a bump at around 300 that appears to be real, although I don't have any kind of explanation for it. So I can't explain why it wouldn't be there, though. So that may be something real that's happening there. The scale height shows a dependence with true anomaly, and basically the farther out from the sun we are, as we go from perihelion to aphelion, the scale height increases, and that's consistent, at least qualitatively, with the increased calcium lifetime as you move farther out from the sun. And so that isn't a surprise. I mean, that parameter isn't quite as surprising as the intercept result. Next slide. Is it going? No. Yeah, next slide, please. So what we know is happening is that all the calcium is coming from a small region near the surface at the dawn equatorial point. It's coming off very hot, at least 20,000 K, probably closer to 50. The source size and temperature don't seem to change much over 8 Mercury years. The source strength is varying with true anomaly. We have a mechanism for producing hot calcium, which is that it's coming off as a molecule, and then when that dissociates, so I'm using Maxwellian sources, but this would be a non-thermal process. But calcium comes off as some kind of CaO, CaS. When it dissociates, it gets a burst of speed that would be equivalent to about 50,000 K in speed. So we can at least explain that, although we don't know why the molecule is coming off. We go to the next slide.
Are you about done?
Yes.
Okay.
I just want to I want to rule out all the things that we think could be happening real quick, because so it's not fixed. It's not related to the surface geology because it's fixed in local time. It's not related to the magnetosphere because it's not variable enough to be magnetospheric. It could be related to impact vaporization, although we don't really know how. And it's definitely, I don't think it's related to calcium freezing on the night side and vaporizing. And if you go to the next slide, it'll show why. As when Mercury approaches perihelion, it stops moving in the sky, and the sun actually stops moving in the sky and begins to move backwards. And so you would expect something night side rotating in the sunlight to cut off at that point, but it doesn't. That's when it's actually the strongest. And so we don't think it's related to night side condensation. So that's it.
We have a couple questions. I think you may have answered one, but Dana Hurley asked, have you tried any non-thermal distribution, and how can the 50,000 K temperature come about? I believe that's probably for calcium. I think you may have answered that, though, in your talk.
Yeah, and I have used some non-thermal distributions. Matching the limb scans with a Gaussian source distribution works really well. like a peak closely to 4 kilometers per second, 5 kilometers per second. Works really well on the limb scans, but I'm not clear that it has a high enough energy tail to get out to farther distances. So I still have to play around with that energy distribution.